Hey guys, in this video we're going to discuss problem 5, Monk and sorting algorithm. The problem states that Monk recently taught Fredo about sorting, and he wants to check whether he understood the concept or not. So we're given the following algorithm and we have to implement it. The algorithm states that we are given a set of numbers and the rightmost digit of each set is at index 1, second last at index 2, and so on. Now here, we'll define a term called chunk. A chunk is a collection of digits where each chunk consists of 5 digits of the number, and if there is no digit at some position, we take the digit to be 0. Initially, we're given that I is 1, so according to the algorithm, we first construct the ith chunk for all the integers in the array. So, let's say that the value of this chunk is equal to the weights of the respective integers. That is, if the chunk is 1, 2, 3, 4, 5, its value will be 12,345. If weights of all the integers of the array equal 0, then stop. This means that all the chunks have size 0 or all the chunks have value 0. Now, sort the array according to the weights of the integers of these chunks, and if the two integers have the same weight, then the one which appeared earlier should be positioned earlier. After the sorting is done and the array changes to a new sorted array, we increment I by 1. That is, we now shift to the next chunk. So, we sorted according to the chunk of digits 1 to 5, then we incremented 5 to 10, and we kept on going until the weight of every integer is 0. For better understanding, let's look at the sample input and output. But first, let's look at the constraints. A of I is smaller than or equal to 10 to the power 18. That is, there can't be a maximum of 18 zeros in the number. That is, we can have a maximum of 4 chunks because each chunk is size 5. Looking at the sample input and output, we see these are the 3 integers. We have an array of size 3. The first chunk of this integer is 5, 6, 7, 8, 9. That is the last 5 digits of the number. Similarly, for the other two, it will be 6, 7, 8, 9, 0 and 5, 6, 7, 8, 9. Now, we have to sort the array based on the weight of these chunks. Now when we sort them, the array becomes this. The first integer remains at the first place, but this comes at the second place because weight of this chunk is greater than the weight of this chunk. So moving on, in the second iteration, we sort this based on the second chunk. Now the second chunk for the first integer is 2, 1, 3, 4. For the second one, it's 1. And for the third, it's 1, 2, 3, 4. So to make a chunk of size 5, we add zeros to the left of these chunks. The weight of these respective integers is 2, 1, 3, 4, 1, and 1, 2, 3, 4. So when we sort them, the final array that we obtain is this. It is based on the second chunk size. Now the third chunk will have no digits for an integer because the size is too small. The third chunk will contain digits from 11 to 15, which is not possible here. So we stop our algorithm after 2 iterations. Now, if we carefully observe the functioning of this procedure, we can find its similarity to the Radix sort function. We know from the tutorials what a Radix sort does. It takes an array, it takes the maximum element in the array, and it sorts the array by sorting it with the place value of each and every place starting from the end. Let's say mul starts from 1. Mul is something like the place value which we are going to consider. So we call the count sort function for array A and mul, and at each step we keep on incrementing this mul. Now let's go to the count sort function. Count sort function takes the array, the size of the array, and the place where we have to start considering from. We know how a count sort function is. We're not going to the details in this video because it's already covered in the editorials, but we'll have a basic look at this frequency of range. Now, why range? It's because the range for integers is 10, as digits vary from 0 to 9. Count sort sorts the array based on the digit value or the place value following all these procedures. So, if we look at the problem statement again, we'll have to implement the Radix sort in a similar manner because at each and every step, we're sorting according to chunks, but the count sort function has to be modified so that it sorts them not just on a basis of position, but on a weight of the chunk. This will become more clear when we start coding the solution. We initialize main int, size of the array, and maxi for the maximum value. We take the numbers, we calculate the maximum value, and then we call some of the Radix functions for this vector v and for the maximum integer maxi. You can see we have declared for the chunk size as 10 to the power 5 globally because there are 5 digits. We declare something called an iter. Now, we have seen an iter is something that states how many positions we have already considered or where do we have to start considering from. So initially, iter starts from 1. We summon the count sort for v, an iter that is considered as the first 5 digits or as the first chunk. Let's start focusing on the count sort function. N is size of the vector. We declare a temporary vector to store the new array because we can't modify the original one. We store the frequency of chunk to underscore size because chunk underscore size is 10 to the power of 5, which stores value from 0 to tetra 9. This is because it's the diversity that the chunk can be in, that is, 0 to 5 nines, because it can be 5 digits. So we keep on storing the frequency of the current position, or the current chunk. Now, how do we determine the current chunk? We divide v by I by iter, and then take mod with the chunk size that is the next 5 digits. This gives us the weight of the chunk, and we increment the frequency for that particular weight. In the next step, as count sorts functions, we store the partial sums. That is, after this step for each I or each weight of the chunk, it will store the position of the ending of that chunk in the final sorted array. This is the functioning of the count sort, and as we now start from the end, we start constructing a sorted array where the position of each and every chunk is determined over here, and frequency of pos minus 1 TMP. This integer here will determine what's the position of this current chunk or the current number in the final sorted array TMP. It is equal to v of I. Here, this value determines the position of the weight of the current integer that it has to store in the final array, which is considered by doing a partial sum over this array. So, we store v of I in that very position, and now after this loop is complete, a TMP array is built, and we have to store it, transfer it to our initial vector v, and print it alongside. So this function is basically the implementation of count sort with just a minor modification that instead of considering one place, we're considering a set of 5 places, or a singular chunk as we call it. Now, looking at the complete function, we take the numbers, we construct our vector, and we take the maximum integer. We summon Radix sort, and at each iteration of Radix sort, iter grows by 10 to the power 5. That is, it considers how many digits we have considered and what the next chunk that has to be considered is. We summon count sort, and then count sort simply functions. We know how to count sort functions, and it sorts the array in every step according to the current chunk size. So when we try and submit this, cool, all accepted.